So I am going now to the second part of my talk. The second part is just vector 1 over non-Kaehler elliptic surfaces. The result obtained by me together with Ruxandra Moraru. She's born in Canada from Romanian parents, but it was not from Romanian school. And she saw my book, which passed the PhD degree with Portuguese in McGill. She saw my book, and because her grandmother was in Romania, in Bucharest, she visited her grandmother, immediately the institute in Mar. Just because, well, somebody appeared in my desk and asked me if I can answer to some question. Then we began our collaboration, and a series of 3 papers to prove several results. I will very shortly I will explain you. Okay, of course, you know that the physical world asks us to take X to be a so-called Calabi-Yau threefold. 3, it's complex, so we have 6. But we take only this elliptic surface, so it's just twofold. So why? Because the result are almost complete. You can say almost everything about the solution. And so if you are interested, let's say for some restriction of solution from that port to this one, you can have examples. Some of them can be computable, not everything, but some of them can be computable. So elliptic means that this X has a map to a curve. So this is a curve, any curve, smooth curve, of course. Now, already from Kodai, now you know if this is non-Kaehler elliptic, then this X is a quasi-bundle. What means this? So all the fiber are isomorphic with the same elliptic fiber. I surely know this elliptic fiber by E. With maybe with a finite number of exceptions. But these exceptions, which are in a finite number, all these exceptions are just multiple of elliptic curve, which are isogenous. So they are quite it's almost a fiber bundle, but it's quasi. Okay. You can, of course, it's simple. You have a finite number of points. So here where you have this multiple fiber, then you can take a finite covering of the curve here. You take the fiber product here. You obtain a Kaehler surface, which is a fiber bundle. So we can use this to reduce everything when this is a fiber bundle. So for us, we have no multiple fiber. So this is a principal. So this is a fiber, and then I will take X over B to be a principal elliptic bundle. Of course, the results are more general, but it's simple to be stated in this case. Well, before that I had the result, okay, a theorem of mine in '93 that the narrow surveyed group of such surface modular torsion is nothing else but the homomorphism of the Jacobian of the curve. Here can be any curve. B, and here is a peak 0 of E. Now, E is an elliptic curve, so peak 0 of E is what we know by E star, which is the dual of this. If you fix an origin, this is a group, fix an origin, this this can be, these are isomorphic which we see. So sometimes I would put E or E star, it doesn't matter. So here it is star. So what is this? So every element in the narrow survey group here, modular torsion, isomorph is here. It's simply to see there's this an element here. If you take an element here, is a class. Let's say is a class of a line bundle. So the class of a line bundle is an element here. But this will give us a morphism here. It's simply to see that this morphism here is nothing else but a section from B to B, which is a Jacobian, simply Jacobian of X. And a section here. Well, that element I have no idea. I prove this using some spectral sequence or some kind of identification. But in fact, this is nothing else but spectral cover of Hitchin for line matrix. So this section is just a spectral cover. A la Hitchin. Of course, when I use it, I have no idea. Okay, now, the most interesting part is we take rank 2. We are in the case of principal rectified boundary. And now I will describe a little bit. Okay, what we did a twisted, I have no time to explain it, maybe in the last part, a twisted Fourier-Mukai transform. And with help of this, we found description of the spectral curve of a vector bundle. So V is a vector bundle of rank 2. And the spectral curve has a form, some okay, side, DI, maybe DI. I'll explain what is this. Some from 1 to K, say, plus, no, okay, yes, to C bar. Okay, I'll explain everything. So BI, between K, there are some points in the base curve here. Here I take some fibers. So in fact I take some fiber because he is I take some fiber from the Jacobian. And here what is C bar? C bar is a divisor here. So I put this result especially to show you. So for a line bundle, or the Cherenkov class of a line bundle, we obtain a section. For a rank 2 vector bundle, the spectral cover is a bisection. Bisection means that this C bar intersects every fiber twice. So in the intersection with every fiber is 2. Okay? So here we have the bisection here. Okay, here there are some part of jump of this vector. What is the idea of this twisted Fourier-Mukai transform? Okay, what is the idea of Fourier-Mukai transform? You want to study the category of shifts here, more general, not necessarily vector bound, category of shift here. And sometimes it's difficult. Now, this Jacobian looks more, has a simple form. It's just a product of a curve with an elliptic curve. Maybe it is easier to study the query shift here. How can we pass from the query shift here to the category of query shift here to the category of query shift here? Well, by the Fourier-Mukai transform. Sometimes you cannot go with a usual Fourier-Mukai, so you have to take twisted shift. So this twisted shift should be taken here. So you have equivalence of category. So you start. The idea is I have a vector bundle here, and I can go into the twisted Fourier-Mukai, and then looking what happens here. So the idea is here I have this bisection, and I have not a vector bundle, but I have some kind of twisted shift, but with a smaller spot. It's hard to be believed, but it's easier to classify these things than to study directly vector bundle. It's at least for elliptic fibrations is only mentioned to study them. And now it's, you will see in a minute that we shall come to a more algebraic geometry problem. So let us fix delta to be the determinant of V and define here.
This means the terminal line bound?
Excuse me? Line bound. Line bound. Well, it's not very happy the notation, but okay. This way. And I define a map in the following way. It's an involution. I do not disturb B, but here I will put delta B. This is a restriction to a fiber. Delta B, and I tensor this. If the restriction, if this will be trivial, it's a usual evolution on an elliptic curve. Lambda goes to lambda dimension. It's the evolution of the elliptic curve. But here it's perturbed. This is perturbed every point by this restriction delta. It's still an evolution, and simply to see the action is very good. So we take this is J of X, and we take the quotient. J of X, we take the quotient. Okay, let's say this is theta, to the quotient J of X by this involution. By this involution. Well, it's not strange. You see, if you take an evolution on a curve and you make this identification, so it's just identification by the action of a group of order 2, then elliptic curve, the quotient by such action is a P1, it's a projective line. So what you will obtain here, you will obtain here a ruled surface. So the fiber P1, and then the same base. So here it's just, I don't know, the notation is very, but it's a ruled surface. Okay. When you say to algebraic geometry that you have a ruled surface, you say, okay, you know everything. Well, not everything, but almost everything. You know about the ruled surface. So you can classify everything. Vector bound, time bound, everything. So you have formulas of almost everything. Okay. Now, this bisection is invariant by this evolution, and it will give you, so this one will give you here, I put A, it's just a section. This is just theta of bisection. And this is a section. So you have section in a row surface, you know how the...
What it means, the part?
No, it's just annotation. I don't like C prime, it's nothing.
Okay.
No. Just to see. If you like tilde. No, nothing. I do not make. Well, in some sense, I take. You see, here you have some points, BI, which correspond to this. But if you want, I take here also. I go over this point also. Okay, and now these fibers are going to fibers in this ruled surface. So we obtain the so-called graph of vector bounding, which is just sum from 1 to k for some fiber. These are fibers in this ruled surface plus a section. Now, this is called the graph of V. And now I can present you the result very shortly. So we have to find a map. So put here and then I will explain. So I obtain a map which take a vector bundle to a divisor here, his graph. So divisor, as I said, divisor on a ruled surface you can describe everything. It's simple to describe, you know, almost everything here. What is this? This means stable two vector bundles of rank 2 with fix the determinant, and fix C2. And stable with respect to some Godushon metric. I have no time to explain it. Now, what do we prove? We describe the smooth part of this. And we give numerical condition for M delta C2 to be non-empty. So we know in which numerical condition we have solution for corresponding Young-Mills equation. The general fiber of G here is just the Prim variety associated to the double cover, B, this is 2 to 1, double cover of this bisection to B. If you have a double cover, you have a Prim variety. So the general fiber is, of course, there are not all the fiber are smooth. This is smooth, and there is a Prim variety, and we give description of singular fibers. Almost every singular. There are, I think, 1 or 2 cases, but the computation too complicated that we didn't finish them. It's not so important because we know almost everything, and the most part of the singular fiber. There are some, and really it was very complicated. Okay. Now, what next? Next, in some minutes. But you see, it seems to be a simple way to find this, but it's not so, because, okay, you can describe geometry also this in a simple way. For the people who know the classification of a pair, this part is composed, when you take the restriction of it to a fiber, you have a vector bundle. When you take the restriction to a fiber here, you obtain a 2 vector bundle analytic curve. And here in C, there are exactly the case where this is semi-stable in the classification of it. And here, exactly the points where they are not semi-stable, so we have jumps. So this part of the graph is responsible for the jumps of the membrane, and this part is for the semi-stable. So this construction, you can describe it, but the construction should be done in this way, because otherwise, so the geometry insists here on the functorial construction. Why? Because you can transfer properties in a right way. If the construction is not functorial, then you have a problem. I mean, you cannot pass from one place to another place. You can pass. So this way. So for this case, okay, let's say we obtain almost everything. I mean, non-Kaehler elliptic surfaces. You have the description of these modular expresses of vector bundle. Now, of course, the next step is dimension 3 or more. Why not? Also, you physicists prove that our dimension of our space should be 10. No? For Minkowski and 6 from this guy here, Barabiov. So who knows? Maybe.
May I ask a question for this?
Yes.
If I understand correctly, this should correspond to some K3 computations at the quadratic extent?
I think yes. I think yes, but it's not a question for me.
Okay.
They said this because we published the paper all over physicists quoted the paper and so on. They took our infraction example from just a construction. Also, yes. Okay. Now, third is just dimension of x bigger or equal to 3. So we take an elliptic, a principal elliptic bundle. So here, okay, let's say S. In fact, the dimension, so dimension of S is greater or equal than 2. This is greater or equal than 3. The fiber is again an elliptic curve. But I will take non-Kaehler. Non-Kaehler, this is very important. Non-Kaehler, okay. Now, we intended to do the same. Here, the result with Elena-Mirela and Trautmann. And we intended to study the same problem, but we are very far to reach the same complexity of the result. I mean, it's much more difficult, and but then only some partial result. It's simple to prove that the Jacobian of X is just B, like in the other case. The problem is this GB correspond to universal problem for some functor, the peak zero relative. So it's peak zero of x, so relative, okay, relative to no b. Yes. So relative to that, peak zero relative, and this functor, okay, I will have more time to define. So this is indeed, well, in some sense, represents this functor, but not in the proper way. It's just a quartz moduli space. So you have not a universal shift. Why you need a universal shift? So a fine moduli space means that the functor is practically given by some home. So from this universal shift you obtain everything by taking inverse image. But it's not so, so it's almost fine. Okay, it's a difference. I have no time to explain that. And we prove that if this is not Kaehler, this implies that it's scarce and never fine. Never fine. So we are forced to work with this Jacobian, but it's not with the final. So we have no universal shift, but we have twisted universal shift. So we have some kind of twisted, I have not tried to explain, twisted universal shift. And then from the category, from the derived category of x, we have a functor to the derived category of this j of x, but with some twist. And this twist, if you try to glue the local universal shift, they exist always. If you try to glue, you cannot glue the shift. You have the relation for gluing the shift, Gij, Gjk, Jki is identity. Okay, it's not identity. It's just this cycle to multiply by that. So it's not a shift. It's so-called, and this is in H2 of G. So I'm very proud of working with higher homology group of this kind. For this shift, it's a very bad. And here is not torsion. If this is non-Kaehler, this alpha is not zero, is not torsion, even not torsion here. Not torsion. So you cannot skip from the twisted part, so you are not in the torsion, so you obtain this twisted Fourier multi transform. And then you try to study vector bundle here by going here. not so easy in that case. Okay, I forgot to say that I put this condition, and this implies this condition, which is a condition of Calabi-Yau. Nothing about the simple connect and so on. So we obtain practically, besides this more precise result, we obtain just one result by taking the moduli spaces of, let's say, totally semi-stable. Or next one, what is totally semi-stable? Semi-stable. When we take restriction, we ask that every restriction should be semi-stable. So we have no jumps, nothing before. And we divide by some equivalence relation, and we describe this with some duality. This is described as some duality space. So I will not use a precise result. The idea is that we can describe some moduli spaces, but we are very far to solve a similar problem like in the dimensional case. And the difficulties are, firstly, we manage the corresponding complex here. I'm starting with the Dirac category with a complex everything is zero, just one vector bound, and then here I obtain only two, let's say F0 and F1. But okay, this acoustic shift you have to work with that. It's not so easy. We have some idea. We try now at least for some particular case, because you see if this is a game, and now I'm finished. If this is again an elliptic surface, the base of a curve, if it's again, you can use the result from this. At least you have solution. Well, pull back the solution from downstairs. So we have some solution. At least so we are looking now to catch at least one solution which are not coming. And I'm sure so I'm sure that there are some solutions, but up to now, if there are at least one, it will be very interesting to have solutions which are not coming from that case. Thank you very much.